easier. And I'm working in a Marine Biodiscovery Center under Professor Pastor Jasper and Raymond Abel. Okay, can I just start? Yes, please. Okay, my presentation today is about secondary metabolites study from extreme environment microorganism. So probably this presentation will be more about microorganism and put a little bit of chemistry. Well, not a little bit, but it's like half. Okay, when you're thinking about extreme environment microorganism, like extreme environment, what's in your thought? Like extreme heat, you're in the sun, or extreme cold, you're somewhere North Pole, Aberdeen. It's quite extreme, at least for us Indonesians. You've been several times in Indonesia. And I'm talking now about my research about extreme environment microorganism because fortunately Marcel has been walking around to the extreme environment, and I don't know, when he came back to Aberdeen, he always brings something with him. So why not? We're gonna do something with it. And hi, Marcel.
Just switch it around if you already finished.
One of the extreme conditions, if you ever thought life on Mars, what's like living in Mars? What happened in Mars? Well, it's really nice to know that actually there's some little part in the Earth that it has Mars-like environment. So it's been studied for several times, and including NASA, they're doing some experiment there to study how can we live in a Mars planet in this outer space. And the interesting part with this extreme environment that actually there's been some living creature there. Although it's quite rare, but this place, Atacama Desert, is the one that really Mars-like, and because the hyperaridity for at least 3 and possibly 15 million years. If you want to find rain or like water there, well, you have to wait 15 million years. And a group in Newcastle is a Professor Michael Goodfellow. They went there and then grabbed something and sediment, and they tried to grow something, and they found there are many of these streptomyces and many of others that's really new. Of course, it's an extreme environment, and no one expecting a living organism there. So they found this new bacteria, and with this isolate C58, well, they give us a few years ago. They give to NBC a few years ago, and Mustafa worked with the strain, and he found new compounds. And he's still working with that strain, and he found dead compounds, so many. And so Maya just found a new lasso compound from the Atacama bacteria as well. But while the old samples come from this area, Jackson, I'm working with a slightly different area. Is in top. What's the interesting part with this top? Because in this top you can find some vegetation. It's the driest place on Earth. Why they have this vegetation? Well, apparently there's a river underground there that move, and then it keeps the vegetation alive. So we were wondering, I was wondering whether there's a new bacteria there. So I'm planning my work. Well, it's a simple plan actually. Get the pure cultures, try to identify them, and then map the organic compounds with relation and structure. Finger crossed. I don't know if I can find new, or it's not new, or probably I won't find anything. That's the worst case. Not really worst case. The worst case is, well, I'm not going to tell you the worst case. Keep it for myself. Okay, so how to get the pure culture? This is the microbiology work. So this is photos of Dr. Anil Saja. She's a microbiologist who's helping us last year. So from the sediment, we dissolve it in a clear water, sterile water, and then we try to grow it in a plate. Then we see there's so many things growing in a plate. Then the first culture, we try to separate it, and then if it's not pure, there's some others contaminant or others growing, and then we separate again. It can be few weeks, it can be few times, it can be, well, it's quite time consuming until we get the pure culture plate. After that, we can grow in the liquid culture. Then we can start to do the chemistry work. So this is my early cultivation of pure culture, and I managed to get some of them. And we made it like top 1, 2, 3, and all of these actinomycetes. And then, okay, the next step is try to identify them. So we're working with another microbiologist from India, Dr. Pratap Singh, and we send it for 16S DNA identification. So before, probably some of you here never heard about 16S. What is 16S? So 16S is like it's like a passport for bacteria, because there's some parts in ribosome inside the bacteria, and they're like really conserved. It's highly conserved that you can tell directly what kind of species they are. So in this conserved thing, well, it's like their passport. They cannot tell you what are they, but they can tell you directly if we open that, see the sequence of the 16 DNA, 16S DNA, then we can, okay, you are this group. It makes us easier. So after we got their passport, so this is the list of 16S identification, and well, it said that the alignment is matched like 99% of those bacteria. But although it's 99%, I mean, you cannot really show that this is the correct one. It might be new one, but well, we never know. But at the moment, this is the best that we can achieve. And it's good enough, 99% and 100% alignment, but it comes from the extreme environment. So we just give it like, okay, this is the first hypothesis about these bacteria, Streptomyces. While we're doing that, in my strain, because I want to grow Streptomyces which produce antibiotic, so we put antibacterial and antifungal agent inside it. When we put inside there, apparently there's a fungi grow as well, and it's really weird. We put antifungal agent, but the fungi, not a fungi, two fungi grow in the plate. So I was thinking this is probably like strong fungi. they don't want to dead easily. I mean, they probably like, I don't know, it's a weird fungi. So I try to grow them. I take them out, I grow them, and this is one of them, Top 5am, and I grow them in two different kind of media. And it's really interesting that you see in these two different media, there are some compounds that produce in one media, this is ISP2, and it doesn't grow in the, it doesn't produce in other media, while this one produce in malt extract ME, and it's not really that much in ISP2. And we check for the 666.2123, which is the exact mass of this compound, that is no hit. So probably it's a new compound, but we never know. Okay, so this is and this is the other fungus. Try to grow it in ISP2 and malt extract as well. And it's quite similar, but there are some like chunk here, and there are some in there in ISP2 that that produce but not produce in malt extract. And at the moment, both of them I have like the crude of the samples is not really that much. So if I want to go further for the next purification, I need to have more. So I try to grow them more at the moment. And when I'm doing the ethyl acetate fractionation with this fungi, there are some LCMS, and this is really interesting because after this fractionation comes like quite pure, so I can move further to elucidate the structure. So this is from those fraction. So it is quite pure, so I can get the elucidate the structure there. And here it's quite nice actually, but the real things happen is like this. It's not really nice. Although Marcel sit down 1 hour and he can finish that, and then what's yours? Okay, I need some time, Marcel. Yeah. So the fraction is this one. Yeah? Okay, you can read it by yourself. It's quite long name, but apparently it's a known compound, and it's already been founded 1991 when I was this high. And at the moment it's new antibiotics, but right now it's not new anymore. Okay, I think that's my next plan. Next plan is collect as many as I can get, and try to get more of the compounds and see what's happened. I mean, I still have chunk of crude, and keep my fingers crossed. Yeah, I have no idea what I'm doing at the moment, but I know what I'm doing actually, but I have no idea what's going to happen. That's from the driest place on earth. Now we're going to the deepest place on earth. I hope I still have some time. Okay.
9 minutes. We allow time for questions. 9 more minutes, 9 minutes.
Okay. This is a Mariana Trench. If you ever heard about Mariana Trench, there's a deepest place on earth. Actually, the deepest place is this Challenger Deep. It's like slightly below Mariana Trench. And it's really interesting to see what happened inside there, because it's the high pressure condition. You know, piezophile, that's what we call a living microorganism there. They can live only if the pressure is high. Then piezo tolerant is a microorganism that can survive in the ambient pressure. and the high pressure as well. While pressure sensitive, you put a little bit of pressure and they're gonna die. So that's the simple from this. And it's still on mysteries. I mean, people make films of it, and they're dying to go there and see what's inside there. Although in the movies, well, it's not in the movies, in the real down there it's only like sand, because who can live with that kind of pressure? But Mr. Wasufato R, they found that there are diversity can be isolated down there. And we're really glad that we have this collaboration, and I'm working now with the MT25 strain. There's one of the microbes inside there. So they take it out, we have it. And in a few years ago, while Abdul Majid has already studied with the secondary metabolites, and he found 6 secondary metabolites and all are known compounds. But I was looking at one of the compounds and see there's one, this NAGGN, is a dipeptide, which is in other journal, it said that this is an osmolyte. So osmolyte, they can cope with the difference of osmotic pressure. Well, if they can cope with if they call osmolyte, could it be they're also a piezolyte? And the reason is it possible that this compound is the key about the adaptation within the deep? So my aim and method is try to investigate correlation between the concentration of NaGGN at different high pressure. Try to grow it from this raw stock, obtain a pure NaGGN, and try to grow them in the high pressure and see about the concentration of NaGGN. So this is MT25 that I grew. And then with several trial and error and how to get NaGGN whatsoever, and I managed to find a good media to produce NaGGN. So on it in this ISP2 with addition of monosodium glutamic acid. So I found it. Well, it came really early in LCMS, but it was really good there, and this is definitely the compound that I'm looking for. So with this high pressure vessel, at the moment I try to grow them in a high pressure, although it's I'm still working on it at the moment. And meanwhile, I try to synthesize as well, do like synthetic chemistry with Dr. Laurent Trombleu, and try to make NaGGN. Just in case if I don't get much NaGGN, I can get it from synthetic. It's still going on. I mean, hopefully it can get, well, I've tried 2 times and it doesn't work, it didn't work. And then the 3rd time, it looks better now. And the future thoughts, so if it works well, then I can prove it. I'm going to prove it like this. So if the concentration elevate during the high pressure increasing, then I will try to knock out, I mean, it's like probably in the future, I will try to knock out the DNA of the NaGGN production and see if they can still live in high pressure. And after that, probably I can take that and take the DNA of the NaGGN, who can produce NaGGN, and then put it in somewhere else, probably like E. coli or something, clone them, and then try to prove if they can live. So I might get this super microbes, or I try to make a mutant X-Men protein microbes. Okay, right. So thank you for all the names there and everyone here. I put many names there. If you don't have your names there, probably I haven't put it the co-workers and all fellows. So thank you.
Any questions?
What kind of pressures can you get in the bathroom? Can you control it?
Yes, so the pressure we're using is we're using pump, and then it's a big, not really big actually, but it's a chamber. So we put it inside and we pump the water inside. So the pressure is with the water, and we're using a MPa as a number, and we use 38 and 56, 28 and 56. I mean, these two, it's quite common in some of the journals. It represents 2,000 and 5,000, 2,500 meters and 5,000 meters deep. Thank you.
Kind of broad question, but what's the impact of the work? What are you trying to impact?
Why I'm interested with the extreme environment microorganism? Because if I go back in my country, there are many extreme environments that I can find. We have volcanoes, we have, well, if you ever heard tsunami in Indonesia, we have many things. We have flood, we have everything. Just mention something. Well, we don't really have snow though. But we have trench as well, and the biodiversity in Indonesia is quite varied. So I was thinking if I can learn all of those techniques here, then I go back to Indonesia and I can make like, okay, if we go to extreme environment, I'm the extreme person that you want. That's what I thought. Well, actually I have some of the samples from Indonesia come from the mud volcano, but I'm not going to tell you. It will take quite a bit longer.
Anyone else? While you're thinking, I have one. When you mentioned Mars and sort of comparing the extreme environments,
Yes.
one difference on Mars, I guess, is that there's a very, very low atmospheric pressure there. Which made me wonder, in your desert samples, is the altitude high enough that pressure, lower pressure becomes interesting?
So in Atacama there are some elevation. The highest is about 5,100 meters.
About 5,000 meters.
Yeah, about 5,000 meters, and they have this vast area there. And the project is NASA and all the work. They're making the biggest like observatorium to see the planet because it's really dry. And there's almost no cloud, and they can see clearly. It's called ALMA.
Yeah.
And well, some samples Marcel already brought that from ALMA there, but we're not working on that yet. But yes, I mean there's some mountains there, and there's goes to the shore.
Right.
I've never been there, but I saw some pictures.
Yeah. One last question from the audience. No? Okay. In that case, thank you very much.
Okay.